Okay, so we're going to try and integrate this function here on the complex plane. So we've got tangent of z divided by z plus 4 all to the power of 3 with regards to z, and it's within gamma. Now gamma is defined as a closed square with the corners at these points. Now I've drawn here a complex plane here with this square on it. So we've got the point plus 8i, minus 8i, plus 8 and minus 8, real axis and the imaginary axis as standard when drawing the complex plane. And these are the corners here as marked. So how are we going to integrate this function here? We've got a trigonometric function in the top. We've got z plus 4 cubed in the denominator. So first things first, we need to find where the singularity is. Now, as this is z plus 4 cubed, there's always going to be a singularity at the point where z equals minus 4, because then we get a point where we've got 0 in the denominator. So that's classed as our singularity. So next we need to define the singularity. So at minus 4 on our complex plane, that's going to be around about this point here, which lies inside our square. And as you can see, this square here, it's a closed square. So it's completely within inside this square. So we'll give ourselves a little variable here, and we call alpha equals minus 4. That's our singularity point. So at minus 4 plus 4 cubed, that's our singularity. So therefore what this is a simple pole of order 3. So simple pole of order 3. So that's going to be quite important. So now on to the integration. How are we going to integrate this? Well, as we have a singularity of minus 4 and there's only one of them inside here, and it's a pole of order 3, we can use something called the Cauchy's integral formula. Now you can use Cauchy's integral formula when your singularity is a point inside a closed contour and it's only got a finite number of singularities. So we've only got one here and it's a pole of order 3. So that fits the bill to use Cauchy's integral formula. So next what we need to do with Cauchy's integral formula, we now use Cauchy's residue theorem. So for Cauchy's residue theorem, what we need to do is find the residue or residues of this function here inside the integrand. Now we've already worked out there's only one point where there's a singularity, it's a pole of order 3. We know there's only one residue here. So Cauchy's integral formula is like this. What we say is our integral, I'll put the circle there so you know it's a complex integral, of a function f of z dz, with all these things that I just discussed in place. We say that this equals 2 pi I, and then here we use a letter for a variable, which is the residues or sums of residues of this function in the integrand. So 2 pi I, for this occasion I'm going to use s. So s equals the sum of the residues. So the residues of this function. Okay, so now all we need to do is find the residues and the value of those residues at our point minus 4. So the residues or residue of our function f at minus 4. That's what we need to find. So I'm going to define our function f is f of z equals tangent z over z plus 4 and cubed. So that's our function. So residues, the Cauchy's residue theorem says what we can do is here is we need to use the one where we can take derivatives, but the important part is the first derivative of this at the point at -4, which is our simple pole, is 0. So we just can't use the version where it's g over z over, let's call it h prime over z, because this h prime over z is still 0, because our z here will give us a 0 inside the brackets there. So we need to use the advanced version of that. So what we use is this one here. I'll write this one down. So it equals 1 over k minus 1 factorial. That's the first part of the formula. Now k, so here I'm going to write another variable up here. Seems to be a lot of variables in this theorem, but very important to our answer. So k is basically the order of the singularity. So in this case, k equals the order, which in our case here equals 3. So 1 over k minus 1 factorial, and then we take the limit as our z, which is the point we're interested in, is -4. So the limit as z approaches alpha, so the z approaches -4, and then what we need is the derivative k minus 1 dz k minus 1. Put a bracket in there, I suppose, just to be 100% technically correct, and make sure this is as clearly as z and not a 2. So basically here we need the derivative of 3 minus 1, which is 2, so we need the second derivative basically in our case here. And then what we do is we have our function f of z and z minus alpha to the k. So basically what this bit here is telling us is that we eliminate our denominator where it becomes 0, so at -4. So basically we eliminate that, and then we're just left with the tangent, which becomes our f of z. Okay, so now let's go through this and just clean it up a little bit. So I'm just going to come across a little bit and carry this down. So now that leads us to 1 over, so k minus 1 factorial. I'm just going to still write what the k is here so we can see what's going on. There's a lot of things going on in this formula. So now I'm going to put the numbers in of the variables. Then after that we can work it out as z approaches. So we've got -4. So that's our limit that we're taking. K minus 1, so that's 3 minus 1. So I'm going to write that in here, 3 minus 1. With respect to z, 3 minus 1. And then we want our function f of z, which is going to just leave us with tangent z. So I suppose technically I should put a bracket around this, but it's as in multiply, so it's all within the derivative. So tangent of z, and then we multiply this by z minus alpha to the k. So basically this is the bit we're going to be eliminating. So yeah, I said I was going to plug in the values of all these anyway. So z minus, and then -4 to the 3. Okay, so now we can just go one further now and just write this out as what we're looking for. So here 3 minus 1 factorial, so that's 1 over 2 factorial, which we know is just a half. The limit as z approaches -4, so now what we'll get is this bit here will be eliminated, as will this bit here from our final calculation. And then we want the second derivative with respect to z of tangent z. So after all that writing, this is the bit that we need. That's going to be the crunch to our answer. So what we need now to progress further is the derivative of tangent z, and then take the derivative again. So I'm just going to come down here and calculate the derivative and second derivative of tangent z. So the derivative of tangent z with respect to z, Now what we know with this is a famous derivative, this is secant squared of z. Okay, so now we need the second derivative. So now what we need is the derivative of this. So the derivative, just write that a little bit neater. The derivative of secant squared z dz. Okay, so by the chain rule, 2 will come out front, and then we've got secant of z, and then the derivative of secant z, which is secant z tangent z. So then we've got secant z tangent z. Okay, so let's get rid of these dots. So now we just simplify this up, and we get 2 secant squared z tangent z. Okay, so now we've worked out this derivative, I'm just going to take this bit off the board, and then we can just continue calculating Cauchy's integral formula. Okay, so I've written our second derivative in here, so now we're clear to continue with the Cauchy's integral formula. So now what we can do is clean this up and put in our values that we've got for our derivative. So then that will give us 1 over 2, that's 1 over 2 factorial, that's fine. And now 2 secant squared z tangent z. So 2 secant squared z tangent z. Okay, now as we're calculating at -4, that's our alpha that we want. That's our simple pole of order 3. So now we're going to plug that in to our function. So now these 2's cancel out, that's pretty good. So now we've got secant squared -4 and tangent of -4. Okay, so there's a couple of trig identities we can use to try and eliminate this minus if we wish. So secant, graph of secant will look something like this. So that's 0, and if you imagine these points here are the pi's, so minus pi plus pi, secant will come down from infinity here, then down here, then off back up to infinity, and the same at these points pi, it will do exactly the same. But it won't touch, these here will be points which will just be undefined. So what we know is about secant is it's reflected in the y-axis. So our point at -4 will be the same as the point at +4. So let's clean that one up. We can say that is secant squared of 4. So that takes care of that, so that's good. And then tangent of -4. So tangent is a little bit different. So tangent will do this kind of thing. So let's just try our best to draw our tangent here. Now tangent, instead of reflected in the y-axis, our tangent function can be rotated fully 180 degrees. So that means our function tangent -4, so let's just write that here, tangent at -4 equals minus tangent 4. So that's our trig identity we can do here for tangent. So now what we can do is bring a minus out front and then tangent 4. Okay, so we're still not quite finished. What we need to do now is to give our Cauchy's residue theorem with the sum of the residues. So this still here is just our residue. So now what we're going to do is our S, this now is our S, so I can take this off here and say S equals minus secant squared 4 tangent 4, and then our integral now, we're ready to calculate it. We've got our integral over gamma, so I'll just write gamma a bit better, over gamma of our function here, tangent z over z plus 4 cubed dz. This equals 2 pi I, and then secant squared 4 tangent 4, and then don't forget the minus in the front. So minus 2 pi I secant squared 4 tangent 4. If we're really fussy, this minus I we can bring down into the denominator and reduce the minus to a positive, and then we have positive 2 pi I secant squared 4 over tangent 4 over I. So we could write that if we like, 2 pi secant squared 4 tangent 4 over I, and that will give us the same answer. But I think I prefer the look of this one, even though it's got a minus. Both have got something that we maybe want to disappear, is a minus sign or a denominator. So anyway, that is the answer to our original question, our integral of tangent z, z plus 4 cubed dz. Okay.